you want any help with QA, or can you handle it?
I should be able to.
Okay. We'll play by ear. Wait. Well, I was hoping it would actually. Sorry, I'm getting talked at. I was hoping it would stay dark and gloomy in here because James King is going to be talking to us about dungeon generation techniques for roguelikes in Python. So let's give him a big round of applause.
All right, thank you. First, I'd just like to thank the PyCon organizers for putting on such a great event. It's my third year running, coming to the event, and it's just been really well. It's been bigger and better every year. And I'd also like to thank the volunteers for making it run smoothly. So a bit about me. I've been a PyCon programmer since about 2006, professionally, but some of my earlier experiences go back all the way to about 2004. My day job is mostly about development operations, web applications, distributed systems, and storage, things like that. But at night, I run a weekly D&D group every Sunday, and I like to design dungeons. I also have poured my heart and soul into thousands of hours of roguelikes. Who here has played any sort of roguelike games? Good crowd. So you know, like Rogue, NetHack, Moria, Angband, and one of my personal favorites, Dungeon Crawl Stone Soup. And in order to become a better player, eventually, maybe if you're also a programmer, you start digging into the source code and figuring out how it's making the levels, where it's placing enemies, and things like that. So today's talk is primarily about designing procedurally generated content for games. And I say designing because when people think maybe random generated levels, they don't think of like carefully crafted gameplay experiences, and they don't think, they think maybe like it's just going to look the same after a while, and it's always going to be not coherent. But in my adventures in exploring the roguelike space and roguelike development, I've come across some neat ideas that I think are cool anyway, that I hope to share with you today. So the first step, baby step, is how do we represent a dungeon in a computer? And for our purposes today, we're just talking about roguelikes, which are two-dimensional, top-down, so tiles. You might think grid paper, you might think of good old D&D tiles. One common way of representing them in Python is these little nested iterators that construct a list of lists. This is sort of a very naive way of approaching it, and we get our list of lists, and then we use two indices to index into our dungeon and look at the different tiles that are there. One approach that I like is packing everything to a multi-dimensional array into a single list. This is sort of how C lays out its arrays in memory and lets you treat a multi-dimensional array as a single data array. So you get just a list of numbers, and you can index into it as if it was a multi-dimensional array by using something called row major ordering, which looks kind of like this. And if you can imagine each row of the grid being laid out one after the other in a straight linear array, that's basically what this index will let you get into each part by giving it an X and a Y. Which is what I do with a library I wrote a while ago to help me out write some demos and things like that, called Horton. It gives you a little grid object, and then you can just index into the grid using a familiar XY sort of pattern in the thing. So first steps with random level generation are mazes. I think it's a good start for anybody who's interested in getting into this topic. The reason being that they're very, very easy to implement, that there are lots of them, and you can get results very, very quickly onto the screen. The first kind here is an example of a DepthFirst search, like a backtracking DepthFirst search algorithm. What you do is you just start off at a random point somewhere in your grid, and you start searching as far as you can until you hit an end, and then you backtrack and start going as deep as you can again. That's where it gets its name. So you can see like there's a little bit of helper code in the background that I haven't explained here just for this is just where it's the core of the algorithm there. So you start off with a stack and a current cell that you choose randomly from your starting grid. The cells, by the way, are the elements inside your array there. I just make them like little dictionaries or little objects that have 4 walls. I guess, and basically we're going to tunnel through each cell as we come across. So we start off with a full stack, and while there's still elements in the stack, we just get the unvisited neighbors for our current cell. If there are some, great. We take a random choice from those neighbors. We remove a wall between the current cell and that random neighbor that we selected, so on and so forth. And we just append the current cell to the stack, choose a new one, so on and so forth. What can end up happening is that you'll get to a place where there are no new neighbors, and in that case, that's where we start popping things off the stack and backtracking a bit until we get. Without getting into too much details of the proof or anything like that, this algorithm is guaranteed to touch every single cell in your grid, and then you end up with a maze like this with long, windy, twisty corridors. A different example, just to contrast the different methods available, is called Prim's algorithm. The Wikipedia definition is kind of dense, but it says it forms like a minimum spanning tree of connected, undirected, weighted graph, and it finds all the subset of edges that connect every vertex. In implementation, it's a little bit more dense than the DepthFirst Search, but if anybody's seen the A* search algorithm, it looks kind of like that, where you have a frontier of cells you haven't visited yet, you have an interior number of cells that you have, and you basically keep adding new cells from the frontier into your interior cells and adding new neighbors and things like that until you've exhausted the entire space. So what's really interesting there is that just by switching the algorithm, we get two different designs for our mazes, and that's sort of like the first knob we can adjust as in code as designers of these levels in these games, is that we can just tweak the algorithm, change the algorithm, and check out its results. So you notice in the DepthFirst Search, there's long, twisty corridors, and I find that in order to find as a player like which branches are not worth following, you have to kind of follow it a little bit with your eye or as you're playing before you can tell which ones are bad branches or not. Whereas with the Prim's algorithm version, you got a lot of short, little, tiny corridors and a very blocky sort of look, which makes it easy to tell which the dead branches are right off the bat. But because it's so dense looking and blocky looking, it's actually kind of a little bit hard to sort of see that flow of movement through the level. Whereas with the DepthFirst Search, I think it sort of gives away the start position, the start cell you picked. But we're not here to talk mazes specifically. At a higher level, we want to generate levels for our games, dungeons. And there are many, many approaches to doing this. One of the more naive ones I've seen, one of the beginning ones that I think are a great place to start, and it will teach you just how complex it can get, is I've got an open grid of just walls, and I make one random room inside that grid, and I'm going to place it somewhere randomly inside. So I've got one room placed on the map now. And my next step would be to choose one of the walls. And I would take out from that wall, I would start scanning ahead until I could find enough room to place the next room on my list. And then if I can, I place that room, connect them up, and keep going. You get kind of branchy looking dungeons that sort of look like interconnected hallways or something like that. But that can waste a lot of effort because there's a lot of edge cases in there, there's some backtracking, there's some checks and things like that you have to do. What I'm going to show you today is a technique that will guarantee that you won't overlap any rooms, so you don't have to do any of that searching, and it generates levels pretty fast. It's called, well, first we're going to start with a data structure, kind of a review for those who've been in computer science before. Maybe you haven't seen this before if you're relatively new to programming. But a binary tree is essentially a finite set of nodes that can either be A, empty, or B, consist of a root with two binary trees. So it's a nonlinear structure, it forms a tree, and I colloquially refer to them as left and right, and so on and so forth. We're not concerned in level design with balancing the trees or anything like that. We're mainly concerned with space partitioning. So this is a space partitioning algorithm. We start off with an open grid. We split it in two, randomly, horizontally, vertically. Where we split it, it can be anywhere in there. And then we recurse on the subparts. And so on the left side, we've split that one into horizontally. And we keep going until you reach either a maximum depth or a minimum size for the spaces, depending on how we want to terminate the algorithm. Sort of the golden rule of recursion is to always have your termination condition up front. Once we have that, we have a bunch of leaf nodes, and that's where we place all the rooms. Kind of interesting, none of the rooms overlap, guaranteed. Once we have all the rooms in the leaf nodes, this is where you want to look up some of the binary tree traversal methods, because we want to go up through the tree in level order. So going from the lowest, widest part of the tree up through and connect all these leaf nodes together at each level. This will guarantee that all the rooms are eventually connected. Some people in my talk syllabus, you might have noticed I said Poisson noise. It was kind of a mistake. There was actually 2 parts to that. I couldn't decide which, and it turns out that in practice runs, I don't think I have enough time in this talk to cover them in depth. But what I did mean was Poisson disks, Perlin noise, and cellular automata. These are a mix of techniques for placing things and also for generating different types of terrain for your levels. For example, cellular automata there, Conway's Game of Life. Everyone familiar with that, roughly? So you have an initial state, you have some cells that are on, some that are off, and you have a couple rules for turning them on and off based on the current state in the next iteration. Run a few iterations of that, and you get caves, kind of cool-looking cave systems. Poisson disks, that is taking a distribution of points inside of a 2D space, or higher dimensional space, but for our purposes, 2D space, where all the points are equidistant to each other based on some minimal distance specified. So that's really neat because you can use that to, like, say, find rooms where you want to place special features, different enemies, bosses, things like that, keys, whatnot. It kind of could be used for other nefarious purposes where the minimum distance, instead of being equal, could be used. You could use a Perlin noise function in there, and then you start getting dots that cluster really hard together. In graphics, we use that to do things like place vegetation, for example, which you could also probably do in your games here. Perlin noise, specifically you want to focus on simplex noise for games, just because it's a little bit more efficient than the original Perlin algorithm. That generates nice cloudy textures. And so each cell will have like a gradient value in it based on all the other cells' gradient values and sort of a histogram of those. And if you have an interval function that sort of takes like the high end off of that, you can have pits and things like that to add to your floor plans. If anybody's played Rogue, awesome roguelike. It has lots of cool little pits with little bridges that span them and neat things like that. Finally, one of the more interesting things that I saw presented at GDC, I think last year, was using constraint solvers for game design. So a constraint solving problem is where you have a bunch of variables whose values could be within a certain range. They could be either continuous or discrete. Continuous being sort of like a floating point number, like an ongoing number that never has a set value, or a finite thing where it's just a set of numbers, like a fixed set will never, there's no, anyways. We want to focus on finite domains for games. It's a lot faster, it's a lot easier, because in constraint solving problems, there's a really large search space, and there's a lot of known NP-complete problems in there if you try to make it perfect. So the fortunate thing is that we're, with constraint solvers, we can come up with an algorithm that is specifically tailored to our problem space, and then we can cut away invalid branches of the search space before we get too far. So the naive version of a constraint solver will look at all the variables and try to reach all the way down and check every possible value for them in every combination. And we can do a little bit better than that. So what does it look like? What's involved in a constraint solver? Well, you have first a variable. Okay, there's more than one usually. And then you have, each variable has a domain of values. And the third thing you need is a constraint on them that takes one or two variables and enforces the constraint on them. So think of the 8 queens problem. You've got, anybody play chess? Everyone play chess? Some people play chess. So you're probably fairly familiar with what a queen does on a board. You place it on a board, and in the 8 queens problem, we want to place 8 of them but none of the queens we place can be in a position where they can be attacked by another queen, right? So if you think of that, that's kind of a constraint problem. In dungeon design, it's more of a, well, I've got all these rooms, here's the exit, I don't care where the end boss is, but I want him to be within one room of the exit. I have all these monsters to place, they can be placed in any of these rooms, and I want to make sure that the room after this one has a health potion. I don't care exactly which room has what, but those constraints must be satisfied in order for this to be a good room for my game. And so we can do that by achieving something called arc consistency. So instead of the naive way of searching all the way through every possible value in the domains for all the variables, like I was saying before, in the 8 queens problem, you might say, well, we don't need to search any row, column, or diagonal once we've placed a queen in that place. There's no future possible configuration where placing another queen in any of those spots is going to make a valid solution. So let's ignore all of those. And in our consistency, we're going one step further, and we're saying, well, let's eliminate all those possible values across all the variables involved in the constraints and just push those forward all the time so that those domains come smaller. We sort of narrow down the domains for each variable as we go along until each variable has a single unique value. And once we have all of that, we know that we have a valid solution, so we can use this level. What does that look kind of like in Python? Well, it's actually not too hard to implement a very naive version of this, just to learn about the general problem, the shape of it, and how to go about it. So the way you might start writing a variable class is just use a set for your values. If you're actually using this in a real engine, you probably should use a bitmask for that, just to make it a little bit faster. But each variable has a narrow function, and the narrow just takes a new set of values, ANDs it with the current set of values, and then you'll see some weird returns throughout this code, and I'll get to that in a minute. But the idea is that if we have values that don't equal the new values, that little save bit is, again, another optimization step where we implement an undo stack. But the important part is to focus at the bottom there. So we go through each constraint in the constraints of the variables involved, and we propagate the new values up to the constraint. And the constraint base class is actually fairly nice and small. This is the entirety of it. It just has to have, obviously, some variables to work with, and a propagate method that has to be implemented somehow. So the propagate method is responsible for taking the new set of values and propagating that down to all the other variables involved in that constraint. And so this is this is sort of sunny pseudocode Python. This is from a propagate method from a hypothetical inequality constraint. Nothing too special there. We're just saying that when we get a new variable, if the variable is unique, we make sure we remove it from all the other variables involved in the constraint. Very, very simple. Right? So this variable x and variable y can never have the same 2 values together if they're going to be unique. This is where we get into some of the edge cases we have to handle. So the solver just has to look through to make sure that once I have all my variables have a unique value, I can stop, return my values, or however I decide to do that. You want to have some undo stack management in there. This is an optimization step. There could be a point where you get to a variable is narrowed down to an empty set, which is an invalid state. The problem can't ever reach a solution. So what we can do is implement a stack that remembers where each value changes in a variable during a cycle, and undo those if we ever get to an invalid state so that we can try maybe again. Just by undoing things. I've lost connection with my thing, so I'm just going to move over here. So these are the optimizations to make this problem tenable. In Python, you want to make sure that you represent your sets of bitmasks. You want to implement that undo stack. You want to use, and when you're actually composing your problems, you want to try to use as few variables as possible, and stay within the finite discrete domain as much as you can. So I want to say thanks again for letting me give this talk. I really hope to see some more games use some of these techniques because there's a large space to explore. And I really hope that there are more roguelikes written in Python in the future. So these are some valuable resources I've found that are worth looking at, particularly how to build a constraint propagator in a weekend. Really good paper. That was what was presented at GDC last year. There's a quick article on some Poisson disk sampling. These two books, Artificial Intelligence and the set of books that are computer programming, really great. If you want to go out and start making your own roguelike games, specifically the Dorian library provides a lot of support in that area. It's a C++ library, but has a nice Python interface. It gives you actually a binary space partitioning tree to develop your levels with, as well as other things like lighting and other neat little tricks that you might want to implement. Horton's my own little library that I've been using. I've been dogfooding that a little bit for some of my demos and the research I put into this talk. And of course, Pygame, Python, and various others. So I think I might have actually run through that a little bit fast, but if we want to open up the floor to questions, there you go.
We actually have a ton of time for questions.
A ton? Oops. Sorry, nerves. I don't think I can today, unfortunately. Sorry.
Where can we find all of those links?
So these slides will be uploaded online with all the other talk slides. You can get those links that are there. These are just short links because they fit better in the slides, but they all point to the resources there. Yeah?
Have you tried anything with, thanks. Have you tried anything with multi-user dungeons, multiple players in a dungeon, and they grow the dungeons, each player grows a dungeon in different places and trying to unify them and that sort of thing?
Right. I haven't yet, but I've been studying Brogue source code very closely, and it's really cool. So that basically means like keeping track. If you're going to start doing pits in Brogue, for example, you can actually like go up to the edge and go over and fall down and go to a new level of the dungeon. And so it's just kind of making it sort of consistent when you imagine putting layers and layers of these things on sheets and then putting them over top of each other, that the holes kind of go line up and you don't keep falling or you hit something or whatever.
Hi. On the slide that you were talking about building the capabilities of each room and whatnot, that to keep the constraints and undo stack, it seemed to me that you could run into a scenario where it was an impossible problem. How do you work around it?
Right. So another optimization technique is to make sure that you only implement constraints that are computationally feasible. You can get into that situation. I mean, in general, like search problems of this nature tend to be exponential in the general case, the general worst case, which is why we try and tailor the algorithms to specific things. But if you're coming up with a constraint that can't be solved, that's a tricky problem you have to try and avoid, I guess. There are many strategies to that. By first checking that the constraints could be solved, you can run an analysis on that. That's a part I haven't gotten to just yet. But there is a good, I forgot to include a link to Logilab's library has a solver already built in Python that you can experiment with and see. A lot of times you just kind of run it after a while and just say, well, I'm going to quit after this and try another one. That might be one strategy.
Oh. How have you worked, how would implementing or using these techniques be better than saying spend a weekend or so and creating N prefab rooms and hallways and then just shuffling them and connecting them together?
Yeah. It's a very popular technique. I mean, Dungeon Crawl does that a lot. They have sort of semi-constructed bits of the dungeon that they connect together. Starbound does that, where their dungeon generation is actually 2D side-scrolling, but a lot of the same techniques apply, where they use pre-constructed bits and connect them all up together. I think it's more of a style preference, where you want like a hand-constructed, made sure that it looks like this type of experience, whereas the constraint solver is more of a, I don't really care what it looks like as long as it remains within these parameters. So it's more of a stylistic choice that you can make. You can mix the two, for sure.
Hi, thank you. Well, that's loud. Just to mention a few things I've been having fun with, I'm also working on a procedurally generated game. In my case, I'm making a game that's like a 2D Zelda from the Game Boy era. And I have the great advantage that there are already existing Zelda games. So in my case, I've had a ton of luck with Markov Chains. For those not familiar with them, Markov Chains are basically finite state machines, except instead of having hard set rules to move between states, you have probabilistic transitions. That is, a state A might have an 80% chance of moving to a state B or a 20% chance of moving to a state C. And then you could do look ahead on cells. So you can have a 1-cell look ahead Markov chain, or a 2-cell or a 3-cell, or however crazy you want to be. So with even 1 or 2 cells, you get really nice results in generating landscapes, things like that. So of course you have to have existing data, but just something to think about. You can have fun kind of making sample rooms and then running Markov chains on those to see what gets generated. And about the previous questioner's idea of doing prefabs, for those of you who are familiar with the game Spelunky, there's an article online that kind of explains how they did it, and they did it in a way similar to that by just having prefabricated rooms, a few dozen per world, and then arranging them in different ways and having constraints on them, like you mentioned. And you get really nice results on that. So there's definitely a large body of work in generating content procedurally that's worth looking into.
Yeah, Rogue Basin's a very good generic resource for a lot of those kinds of articles, gamedev.net, things like that. Starbound guys also have a few blog posts about how they did prefabs and things like that, too.
Thanks for the talk.
Thanks for having me.
I might do it. I need to get something presentable running, and I might do a lightning talk on it, yes.
Do it. More games in Python.
So another question. How would you transition some of these techniques to generate 3D worlds, or generate or layered dungeons? Dwarf Fortress world comes to mind.
Right. So a lot of the algorithms I've mentioned are n-dimensional. They can be generalized higher, like the Poisson disk selection, a lot of the noise algorithms, even something as low level as how you're going to store all your cubes or nodes or whatever in 3 dimensions. So those algorithms will scale up with you when you go up to 3 dimensions and things like that. Like Minecraft, for example, will use a noise generation technique to carve out the caves and things like that. Right, the interpolation. Right, so the cellular automata thing too for generating caves, you can interpolate maps one over top of each other so that you can like sort of get a crumbly sort of effect of parts of your dungeon. That's what I was thinking with the Perlin noise generator. You kind of take only the highest values above a certain threshold and use those cells as, say, pits or caves or just floor, and just kind of make it all mangy and like it's sort of semi-destroyed. Cool. Tons. I could talk games all day. I'll try and repeat the question then. Oh, okay.
So more on the the generation of the 3D worlds ish. Have you generated any sort of ruins, kinda like more of a like variations on the on room structure? Maybe using like creating a room and then destroying it a little bit or rolling it.
Right, so you might use some sort of noise function to kind of destroy it a little bit or change the tiles. With the Poisson disk sampling and using the Perlin noise to cluster the dots together, you can sort of get a vegetation placement, things like that. And for feature selection, things like that, you would add that to a constraint propagator as well, to make sure that like this aqueduct flows through the rooms and is always connected or something like that.
And have you used these techniques for map generation, for like generating other sort of content, maybe creature generation?
I haven't touched on creature generation or anything of that sort yet. It's mainly for maps, for levels, things like that. With a little bit of creativity, it could be expanded out perhaps in that area, but I haven't researched that terribly far yet.
And just out of curiosity, what are the dimensions of the most complex map, or the one that you feel the most proud of that you've generated?
There's a neat technique for the Poisson disk sampling that came out in SIGGRAPH in like 2006. And it introduces a very specialized data structure, like a spatial data structure for fast sampling, because that's actually a pretty slow algorithm to run. But it does it for very fast sampling, and you can get like 17,000, 18,000 points on a very large image pretty quickly. Really quickly, actually, for Poisson disk sampling, just within a second.
All right, let's all give James a huge round of applause. Thanks, James.
Thanks.